1.7, we're going to learn a few special matrices. Can you recall that what kind of special matrix we learned so far? Do you guys remember? No, that's not. That's just a Gaussian is just a process to say it again. Elementary matrix, right? Okay, that's one of them. What else? Anyone? Identity. Okay. So you learn two special matrices, right? Identity and elementary matrix. And both have a very special character. What they do, they have. They are both what? Invertible, that's right. Now remember that, okay? They both are invertible, identity matrix and elementary matrix. Now today we learn a couple more, okay? So the first special matrix we're gonna learn is called for today, okay? It's called the diagonal matrix. Okay. So what's diagonal matrix? Diagonal matrix is like this, okay? You have matrix. And you're going to have a number like D1, D2, and Dn. Good morning. So they're gonna have the lower zero triangle, this all 0, 0, 0, and so on, okay? And then they also have an upper zero triangle. So this is 0, 0, all the way to 0. So the only thing they have is this one, that's a row, okay? Now this can be all 0, it can be 0, okay? But we don't care. We just care about the lower triangle 0, upper triangle 0. Whatever number they have here, we don't care, okay? So your D1, D2, or I should say like this, DI. DI means one of the D, okay? Any number. This is number here. Any number, but this has the lower 0, all 0 here. So this is called a diagonal matrix. This is the third special matrix you learn, okay? Now remember, when you do your work, you want to use a special matrix. You don't want to find just any matrix because the special matrix gives you a lot of character, okay? So what kind of character did they give to you? Okay, so diagonal matrix, we usually use a D, a big D, okay, which stands for diagonal matrix. D is invertible if only if none of D equals 0, okay? Okay, no D equals 0 here, okay? If none of these diagonal numbers are 0, then it's not a invertible. If there are none of them are 0, then it's invertible. You guys follow me here? Any question here? Now, let me give you example. Like examples. Is this a diagonal matrix? Yes, because the diagonal matrix I just had the lower 0 triangle, upper 0 triangle, right? As long as I fit in, then it's a diagonal matrix. But this matrix is not invertible. Why? Because this is 0. You guys follow me here? So this is a diagonal matrix, but not invertible. Okay. So if I give you this, is this a diagonal matrix?
Yes.
Yes. Invertible? No. Okay. Same as that, okay? But what about this one? Is this a diagonal matrix? Yes. Invertible? Yes. That's right. Yes, and invertible. Okay. So this is the third special matrix you learned so far in this class. You're gonna learn more, okay? Why? Because the computer engineer, they don't want to keep searching for matrix. They want to find the one that works for them. So they instead of go searching it, they go pick the one that it works for them. Okay. So this is the third one you see. Now, what kind of special about this matrix besides the invertible? If it's not zero, then it's invertible, right? And they also have some kind of special thing also. First of all, when you power a diagonal matrix, so power D. I just put power D, okay? I don't want to write so much. If I want to power the diagonal matrix here, okay, so let's say D is equal to, I just make it easier, so it's a 2 number, okay? D1, a 2 by 2 matrix. And if I want to take the power for D, now remember last time we did the power before, right? We had to multiply the matrix how many times? That remember that? Okay. Now you no longer need to do that. You just need to power the diagonal. Okay. You guys follow me here? You just need to power the diagonal, then you're done. And like that last time we had to multiply the matrices 3 times, remember? We did on the problem, right? You don't need to do that anymore. Okay, like that's a good thing about diagonal matrix, okay? And there's another good thing. If you're gonna take the inverse of it, if you want to take the inverse, okay, all you do is just flip the number. And then you're done. And there's another good thing about diagonal matrix. And if you have power, okay, and you just need to okay. So there's a lot of beauty about diagonal matrix, allow you to do a lot of things. A night before they are very tedious, right? Now you don't need to. Okay. So let's see some examples. Let's look at problem number 7. Number 7. Okay, you see it there? Okay, number 7. Number 7, a is equal 1, 0, 0, negative 2. You're looking for a squared. Okay. One zero zero negative 2. Okay, and we look for a few things. Okay, first we're gonna look for a square. We no longer need to multiply the 2 matrices. What do we do? Because this is a what? Diagonal matrix, that right? Yes. Okay. So what we do, we just power the diagonal. Okay. Just power it, and then what do we get? Any question here? No? Okay. And the next one is a negative 2. Well, a negative 2 just equal to flip this number, is that right? Okay, you can see how good it is for diagonal matrix. Okay? It allows you to take care of a lot of things, not in a long way, okay? It's an a negative k there, right? The a negative k, can you guys see it? Right, the last one, right?
Yeah.
Okay. It's too early for you guys, huh? Too early morning. But springtime's supposed to come, okay? So springtime you usually get a little bit early too. So you just take this one, just a one. This is just a one. First one, just a one. 0, 0, -2 to the negative k. So it's 1 over. Okay, so that's it. That's it. So diagonal matrix is very good. Okay. Any question here so far? So these are the third special matrix you learn, right? Identity matrix is also diagonal matrix. Anyone? Identity matrix is it also diagonal matrix? Yes, right? Identity matrix is a what? 1, 1, 1, 1, 1, right? Just all the diagonals equal 1. Okay. And the second special matrix called triangular matrix. Well, we learned triangular matrix before actually, okay? It's just that you get a matrix, you're gonna get number here, number. All these are numbers here, and then you get 0 here. Okay? It's all 0. So if you name it by the upper triangle, you call the triangular matrix. If you name it by the lower triangle, you call the lower 0 triangle matrix. Okay? So usually people call upper triangle. That's what they call. It means that the upper triangles are non-zero. It can have 0 inside, but has a non-zero number here. But the lower triangles are 0. Okay. So this is called a. If you look at some of the book, they call UT, upper triangle. Okay, I think that's what they call. And then you have a lower triangle called LT. So lower triangle just like that. Number here, number, these all number, these all numbers here, and then you're gonna get 0 on the top, okay? And you see that they call lower triangle called LT. Sometimes you read some of the book. They say create a UT. That means create upper triangle. That means a lower 0 triangle. Okay, that makes sense to you guys. So this is another special name. Okay, the third special matrix we're going to learn is called a symmetric matrix. There's a lot of special one, okay? So I suggest you guys to, if you when you get home, you have time, you should, because this is your career, right? And you should get a notebook, summarize all these special matrices there, okay? See what they do. So that way later on, if you need any of them, you can look at easily, okay? Find the one you want. So number 3, we have called a symmetric matrix. Okay, symmetric matrix is for, I think it was this is only for square matrix only. Let me check. Yeah, because there's so many matrices. Sometimes I forget there's so many, and I don't use it. I don't use it because I use the matrix for computer. You know, any student here attend for the Cal State Long Beach? Anyone? Okay, you need to be careful now. Long Beach just change the requirement on Math 2, or you're not Math 2 student, huh? If you're gonna take Math 2, okay, they make it harder now. They put in a Fourier transformation in their Math 2 program, okay, in the math program. So if you're gonna change the Cal State Long Beach, they won't accept our Math 2. That's it, they won't accept any Math 2 from any computer course, because the computer course we don't require to teach Fourier transformation because we teach Laplace. Laplace only included, but they specifically say you got to have Fourier. I don't understand that part. I mean, the Fourier transformation is supposed to be like this: the Fourier and then to Laplace, the level. Okay, the level thinking the Fourier to Laplace. Normally, if you teach Laplace, you including the Fourier, but now they say no, you have to teach Fourier and then Laplace. So they put in a new requirement, and then plus they put in a computer programming there. You got to know program, like little bit coding on the class for the math too. So, it looks like Mr. Drake sent us an email yesterday. It looks like what they do is that they combine their upper division, some of the engineering math 2 into their math 2, normal math 2. So that's what they do. Like, because the Fourier transformation and then the computer coding, those are only required to teach in the engineering courses for math 2. But they put into their lower division also. So then now, if you turn to Cal State Long Beach, they won't accept it anymore. So that's why my math 2 class, I have a 2 student job because of that. They said they won't accept it. So they have to take it over there. Because we don't have a computational programming for math 2 here, no. So they require algorithm math, computational math 2 also. So it's tough. So it looks like, Mr. Drix, it looks like they combine the two, upper division math 2 and the lower division math 2, combine some of the material. But anyway, if you don't transfer there, then you don't need to worry. Okay. UCLA, anyone transfer UCLA? Like UCLA, apparently they're doing the same thing. UCLA is doing the same thing. So UCLA and Long Beach are 2 schools doing the same thing. For math 2 only, math 2, okay? Math 3, they haven't done anything yet, but who knows, later on they might say, oh, we require computer. Our math 3 covers everything already. So, but then in case they put in like, oh, we're going to require coding, then we're in trouble because we don't teach that for math 3. Okay, symmetric matrix has to be a square matrix first. Okay. Have a square matrix, okay, and they said if A should equal to AT. If only if A is symmetric. Okay. So if a matrix equal to the transpose, okay, if a matrix equal to transpose, then this matrix is symmetric. So what does symmetric matrix do to you? There's a lot of things they can do for you also, okay? And we will learn about that later on. So that's the 3 special matrices. Now, let's do some exercises. So let's look at this way, okay? I did do it in class. Number 20, just look at the matrix, okay? Tell me, can you guys turn to number 20? Just inspect, okay? It is a invertible. I didn't look at the answer. It is an invertible. Don't look at my answer. Or you can look at my answer and say, why is it yes? It is an invertible matrix.
It has a LT or a UT.
Upper division, right? Okay. Not upper division, sorry. Upper triangle, right? So the importance of this part, the main diagonal, okay? If you have upper triangle, the main diagonal not equal none of them number 0, then it's an invertible, okay? So for the triangular matrix, so if you want to look for the, I don't know if you guys remember when we do our Gaussian elimination, we have this is create a what? Lower 0 triangle, so that is what? Low echelon form, right? For low echelon form, once we get to here, if this is not 0, we will get answer. Remember? Okay. So when you don't have any 0 here, you're gonna get you'll be an invertible. Okay? You get inverse. because these are all pivot position, right? All pivot number, and you can make this to be 0, so you can become a what? Row echelon, reduce row echelon form, right? If you reduce row echelon form, you are inverted. Okay? So they just want to inspect it by just looking at the knowledge you learned from the previous. And then the next one is number 22. So let me scoot down a little bit. I put down no there. Why is it no? Number 22 is not invertible. How come? You have a lower triangle, LT, there, right? What happened to your LT here? You get a what? A 0 here, right? So that means this one, 0 cannot be a pivot. Cannot be a pivot number. So that means you're going to get a free variable here. Okay? When you solve this equation, you're going to get a free variable. So that means you're not invertible. Only the pivot will give you an answer. This will give you a free variable. Okay? So it means you have set x3 equal to t, something like that. Is that right? So then you are not invertible. So that's for number 20. Number 26. Number 26. And let's see what the answers do. Okay. Right here. They find the values. Number 26, they said find all values, the unknown constants for which A is symmetric. So I write this on the board. And here our matrix is so here's an A. They say find all the value of A, B, C, that this one is an inverted, this one is symmetric. So symmetric means what? A is equal to what? AT, that right? U equal to your transpose. So in order for this equal to be a symmetric matrix, so this one, this A is equal to AT. So what's the AT here? AT be what? You flip them, that right? 90-degree flip, okay? So 230. And A minus 2B plus 2C, 5, and then negative 2. And then 2A plus B plus C, A plus C, and then 7. So that's your AT. So you're supposed to make them equal to each other. Now you need to solve this. Which equation you say you're going to create? Anyone? This is equal to what? 3, that right? Okay, so A minus 2B plus 2C equal to 2C equal to 3. So that's your first equation. Anyone else? That's only equal, right? What about this one? This one's equal to what? 0. So that's a good one. So 2a plus b plus c equals 0. Is that right? Do you guys follow me here? Do I need one more? Because it has 3 variables, 2 equations, you need one more equations. Which one?
C is equal to -2.
A plus c equal to what? -2, is that right? Okay, so now let's see. Can you solve this equation? You can use elimination. You don't need to use the Gaussian elimination. You can just use the normal elimination. Okay. Looks like this one has no b, right? This one has no b here, so you might want to take away your b. Okay, you count by 2 here. Okay, then you're gonna have a 4a plus 2b plus 2c equals 0. Add them together, then you're gonna have a 5a. Okay, these two add together. These two become 0. These two become 4c, and equals 3. So you get 2 equations, 2 variables. Now you can take one of the way, so you can times this by -5. So you get -5a minus 5c equal to 10. Add them together, that's gone, so -c equal to 13 and c equal to -13. Okay, so that's the first one. And then you go back to get the a. Then your a will equal -2 minus the c, so equal to negative. So equal to 11, positive 11. And then after that you get a b. To save time, let me tell you what I get for b. B is equal to -9. Okay, so my equation solution for a is equal to 11, b equal to -9, c is equal to -13. So when you have these 3 numbers, this matrix should be symmetric. Okay. Any question here? So when you solve, just because you are in linear algebra class doesn't mean you cannot use your normal elimination to do the problem. You can, okay? It's just they teach you more tools. In the exam, I will let you know what method I want you to solve, okay? Any question here? If no question, then let's look at problem number 28. Let's see what they said. 28, they said, find all values of x for which a is invertible. Okay. So number 28. We are given a matrix A is equal to x minus 1/2, 0, 0, and then x minus 1/3, and 0. X squared, x plus 1/4. Okay. If you want a to be invertible, what do you think your x is equal to? What's the main thing? Invertible. We did that earlier. So when you have what kind of triangle do we call? Lower triangle. Is that right? Okay. So you have a lower triangle here. And for this to be invertible, so that means what? The main diagonal should be what? The main diagonal what? We did the inspection problem earlier, number 2022. So what is it? The main diagonal has to be what? Anyone? Non-zero. That right? We just did that problem, right? So that means what? This is the main diagonal here, okay? It cannot equal 0. No number should equal 0. Not even one of them, okay? So x don't equal to 1/2, x don't equal to 1/3, x don't equal to -1/4. No 0 in the main diagonal. Now this is called the main diagonal, okay? So if that happens, then they're invertible. Okay. So that's basically 1.7. So 1.7 runs 3 special matrices. Okay. We run diagonal matrix. We run lower triangle, upper triangle. Okay. And then we run. Did we run any asymmetric matrix? So we run 3 special matrices. Besides the 2 you add on earlier, right? Identity matrix, right? And then elementary matrix. These are all very special, okay? What's special about them? Can anyone tell me?
The main diagram.
They're nicer. I like that. They're nicer. So you look at, oh, that's very pretty, huh? What's the main thing we like about them? Some of the operations are easy, but that's not the main thing. What's the main thing? The major things. It's because there's a chance they're invertible, that right? Most of them are invertible, isn't it? Unless you have a what? A base diagonal equal to 0, right? So invertible is very important. How come? Why do we need to care about invertible? Did you guys go home and practice? Did you guys review your note? Okay, we talked about that last time. What's important about invertible? If someone asks you this question, how you can answer them?
Because it's easier to work with 1s and 0s.
Not exactly. Anyone? You can divide a matrix. That's the most important thing, okay? Remember, elementary row operation does not have a division, right? But how are you going to divide a number? Easy. But divide matrix, not easy. Okay, then you must need the invertible to have you are able to divide a matrix. Guys, follow me here. So what you learn is not just about getting a grade or finish your class. It's to understand what you're learning and what's the purpose about what you're learning. Okay, that's the most important. Otherwise, you're not prepare yourself very good. Okay, I was watching this YouTuber. He mentioned that Silicon Valley, for the 3 months, they lay off a total 36,000 engineers. Basically, it's all computer engineer. Okay, I watched a lot of YouTubers. They all computer engineer. They get laid off. I didn't hear for other engineers. Okay, other engineers seem to hold the job very good. I think the reason why one of my students is right now he's working here. He's a computer engineer. He already have a degree in master computer engineer, and he work here. Yesterday he came to my office to fix my printer. Well, my printer broke, right? So I called him. I said, hey, can you? He's here for 7 years. He graduated bachelor 7 years ago, get a job here, and then he was my student from calculus. That funny. And he said, yeah, so you never know. Maybe I see you guys one day, right? It happens. I have 2 or 3 students are working here right now. So yesterday he told me, Miss Johnson, I'm so thankful I didn't get a job in the company. I tried to apply it 2 years ago, but no one hired me. He said, it's kind of good because now all my friends get laid off. Computer engineer all get laid off. He said they all get laid off. It's because the last 2 years they hired a lot of people during the pandemic because the what's that called, the pandemic stay home work, right? They hire a lot of them. Now the people go back to work, they don't need that many people now, so they lay all them off. That's what he told me. He said I'm so glad I didn't get hired. He said so I can stay here, so he ended up staying here. So staying here is a little bit stable for him. So sometimes the bad news is a good news, and good news is bad news, isn't it, huh? That tells you that, huh? That's why I also tell my students, if there's something bad happen to you, don't think it's bad, maybe a good thing waiting for you. You just never know, okay? You just never know. So don't jump to conclusion until you show the fact. That's another 1.8 now. Okay, we're gonna